Okay, so let's go ahead and wrap this up. There's three more functions that we have to find the inverse for. Since they're given as equations, we know that the inverse has to be another equation. So we're going to go through our step-by-step process to basically find it. And then we'll do some comparisons and look at some nuances and build to one more topic before we finish. So again, the way we start this is we replace the f of x with y. All right, so again, that one is not too hard to think about because that's what f of x is. But then, right, to start creating the inverse, we flip-flop where x and y are in the equation, right? And so as soon as I do that flip-flop, this equation and this equation are different, right? Because one's input, one's output, and we reverse that information. So we now are looking at an equation of the inverse. The problem, though, is we want our inverse to be a function of x. So we basically have to solve for y here. So I think our first move would be to raise both sides to the third power. That gives us x cubed equals 2 minus y, right? Subtract 2 from both sides. We basically get a negative y equals x cubed minus 2. And if we multiply both sides by a negative 1, what we get is y equals a negative x cubed plus 2. Or we can write that as 2 minus x cubed. Maybe that looks a little easier. So there is our inverse function, right? So 2 minus the x cubed is our inverse function in that situation. So again, how do we test that? We can compose it. We can look at data tables. I'm just going to quickly look over at a graph to see if we got it right. So what we're graphing here, so here is the f of x, right, in red. So that's our cube root of 2 minus x. And then here's the inverse that we found, right, 2 minus x cubed. And they do, in fact, behave the way they're supposed to, right? This S shape is mimicked down over here. There, by the way, the black line is y equals x. So we're symmetric about that line. So it seems like we did our job correctly. So, right, so I guess gold stars for us, right? So what about the next one? Well, again, we begin our journey by replacing the y, or replacing f of x with y. And then what I do is I flip-flop those roles. So wherever I see a y, I replace it with x. And wherever I see an x, I replace it with y. And we now have the inverse. Problem is, though, it's not a function of x. So we got to do that. So using another pen, I think, how about we clear the denominator out? All right, so that will give us y plus 2 times x equals 3. If I now divide both sides by x, I get y plus 2 equals 3 over x. Subtracting 2, we get y equals 3 over x minus 2. So there is our inverse, right? So the inverse is 3 divided by x minus 2. And again, we can verify that by going our compositions, looking at table values. I'm just going to go ahead and look at a graph. All right, so here's my Desmos. There's the line y equals x. So there's our first function, right? So that's the graph of 3, right, divided by x plus 2. It has a nice vertical asymptote at negative 2 like we expect. And then here's the inverse that we found. And you can see, again, it's a little hard to see it sometimes, but that red part is reflected through that part here. That red portion is reflected there, and vice versa. All right, so it does seem like it does what it's supposed to do. So we definitely found the inverse with respect to all that. All right, so the next one, again, following our rhyme and reason, we're going to replace the f of x with y because that's what it is. We're now going to flip-flop their roles to start creating the inverse. All right, so that technically is the inverse equation, but it's not in a good form. It's not in terms of x. So solving for x, perhaps adding 3 to both sides, we get x plus 3 equals the square root of y plus 2. If I now square both sides, we get x plus 3 squared equals y plus 2. If we subtract 2, we end up getting that y equals x plus 3 squared minus 2. All right, and so right there appears to be the inverse, right? And so when we go graph this, let's go check this. All right, so let me turn those ones off that I had earlier. make sure I got, so there's y equals x. Here's our function, right? So there's the function square root of x plus 2 minus 3, right? And then here is what we found to be the inverse, all right? And visually, graphically, we have somewhat of a problem, right? Because what our inverse isn't even 1 to 1. And the reflection here doesn't seem to be a true reflection. So, you know, what's wrong with our inverse, right? And this goes back to what I said at the very beginning, and we've seen a couple times. When we have a function that's not 1 to 1, what we have to do is restrict the domain. And so when we restrict the domain here, what ends up happening is we end up getting, right, so let me go ahead and turn this guy off, and I finally found out how to restrict the domain on Desmos, and there's the domain restriction. What I'm going to do is I'm going to let x be, greater than -3. Let me zoom in there so you can see that that's -3. So if I if I just take our inverse function and just turn it on for x greater than or equal to -3, then I truly have a reflection. So this is called restricting the domain. We have found the inverse, but that inverse only works if we consider the domain x is greater than or equal to -3. If we consider any other part of the domain, like we did here, right, if we now do that part, right, we truly don't have an inverse. We're going to run into that situation that we had a couple of videos back where I think it was a different function but same idea, where we kind of had an inverse for one, but it didn't quite work out for the other. So again, at that point in time, we found we had to restrict the domain, and this time we find that we have to restrict the domain in order to have the true inverse situation. So I'm going to address this a little bit more in another video coming soon, but right now what we definitely have, right, is the fact that we do have a strategy to find the inverse. So if we're given as a table, the inverse is simply a table where we flip-flop values. If we're given a graph, we reflect that graph through the line y equals x, or just manipulate table of values. If we're given an equation, we have a strategy, right? We replace f of x with y, flip-flop the roles of x and y, and then solve for y, and we have our inverse, right? At least unless we have a little nuance like we did in that last one. But I think we've seen that 3 times, at the introduction, kind of midstream, and here at the end, right? Let's hit this one more time about a 1-to-1 function and worrying about that inverse, or excuse me, that restricted domain. So one more video coming soon where we address that, and I'll see you guys then.